All right, so we're going to start looking at equilibrium. I've mentioned this word a couple times, and we're going to go into what exactly equilibrium means. So to this point, we have all the reactions we looked at, we are assuming go to completion, like they totally go through and it's done. So for instance, in this, A plus B equals C plus D. Think of single replacement, double replacement. We're assuming that if you add these two, you're going to get these two, and that's it. Like, that's all that's going to happen. Well, completion actually does mean initially the system contains only A and B. Over time, A and B are used up, and you're left with C and D. When the reaction is complete, only C and D remain in the system. Well, in fact, many reactions do not go to completion, but rather approach a state of equilibrium in which both the products and the reactants are present. So for instance, A plus B goes to CD is better represented as A plus B back and forth between C and D. So equilibrium occurs when you have opposing reactions occurring at equal rates, and the concentration of the reactants and products are no longer changed. Okay, so a simple physical equilibrium. So looking here, we've got three different containers, closed systems, and we have some type of liquid at the bottom. What we notice is right here, only evaporation is going on. Okay, well then right here we have mostly evaporation, a little bit of condensation going back on. And in this one, we have equal amounts, evaporation and condensation happening at the same time. Again, initially, only the forward reaction occurs, evaporation. And then when a significant amount of the vapor is produced, right here, the vapor molecules hit the side, collide with the side, and then they condense back into the liquid state. Eventually, over here, you have the rate of evaporation and condensation happening at the same time. Okay? So other physical equilibria. When heat is added to ice, it melts. When heat is removed from water, it freezes. So if heat is neither added nor removed from ice water at 0 degrees Celsius, stays 0 degrees, it will remain in the solid liquid state equilibrium, with the amount of water and ice remaining constant over time. Both processes continue to occur, but at equal rates. So here you see the rate of the solid is the same as the rate of liquid, which is the same rate of melting and freezing. At a constant temperature of 100, that's boiling and vaporization, versus condensation, you got the rate of vaporization equal the rate of condensation. A saturated aqueous solution shows the following at equilibrium. So take salt versus aqueous salt or salt water. The rate of dissolving equals the rate of recrystallization. So going back into that solid form at constant temp. In a chemical reaction, we've got this chemical reaction. We're going to see this quite a bit. So you got nitrogen, hydrogen, gives you ammonia. Initially, when nitrogen and hydrogen are combined, the reaction proceeds to the left and forms ammonia. As ammonia accumulates in the system, I don't know why it says left. Okay, so I think it should say right. It forms the product. It should go proceeds to the right. Okay, forms the product ammonia. As the ammonia accumulates in the system, these molecules start colliding with each other and reform into the reactant, which goes in the reverse direction. At equilibrium, the rate at which it occurs is equal. Equilibrium does not mean the amount of the products and reactants are equal, only that the rate of formation are. So when is equilibrium reached? So looking at this, you have all of these different types. How do you figure out if you get molecule diagrams like this? What you want to do is you want to count to see that you have the same amount of reactants, like the same number of reactants as the same number of products. And this one will work. When you count them up, you got 1, 2, 3, 3 double at 6, 1, 2, 3 double at 6, 6 and 6 is 12. Then you count these out and you should have 12 combos. All the rest do not. All right. So equilibrium, A to B, B to A. At equilibrium, concentrations may not be equal. So looking at these, you have different concentrations, but they hit equilibrium as soon as the rates equal out. So you have this flat rate right here. When you get the flat rates, that's when they are equal. So concentration doesn't matter. The rate is what matters. You can see the rates are equal right there. That's when equilibrium works or is reached. For this one, you can see that the concentration is lower here where it's higher here, but it's the rates at which they are equal is when equilibrium is hit. So the Haber process, we're going to see this a little bit later. Nitrogen and hydrogen produces ammonia. At equilibrium, the relative concentrations are different. You've got hydrogen and nitrogen have two different concentrations, more hydrogen than nitrogen, but there's more ammonia than nitrogen also. Doesn't matter. The rates are when we're looking at, is when we are looking at equilibrium being achieved. Okay? All right, so this is it for this section. If you have any questions, please don't hesitate to ask. And I hope you guys have a great day.